Okay, let me start to share. Okay, you can see the full screen, right?
Yep, we see it.
Okay, cool. So thank you for the introduction. I guess I get this invitation 1 month ago, and you know, I'm honored to give the introduction here for the transmission electron microscopy. Before I go ahead, I want to have a self introduction. I think work on myself. So I started a PhD, from 2012 in Shirley Meng's group, and also after graduation, during the PhD study, I also worked in the Oak Ridge National Lab as an internship. And for some of you, if you know the CNMS Center, it's a center for microscopy study. And from there, I learned most of my most of the microscopy techniques. PhD study. If you are interested, you can search her work on the website. And after I finished the PhD, I worked with Shirley for the postdoc for almost 3 years. And now I'm a project scientist. So my personal research is on the energy storage systems, especially focused on the diagnosis. For those advanced characterization tools, TEM is one of them. So I spend quite a lot of time on the TEM today. But I personally also interested in some AB initial calculations because for interpretation of the experimental data, no matter it's from the microscope or the spectroscopy, you sort of need the AB initial calculations to better interpret the data, right? So, and if you have any questions about my today's lecture or have other interest in my research, feel free to email me. This is my email address. You can also check my. With that, I think we can go to the today's content. So I want to recommend the books. So for all the techniques, I think the first step, if you want to get into this field, you have to study from the books. Right? I will recommend you to study from books and then read papers and then get some hands-on experience. I find it personally very useful. So those two books I read, I don't know how many times, but I think those are the kind of Bible for TEM field. So one book is for the transmission electron microscopy. So this one is focused on the microscopy itself, right? So taking images, in other words. And the other one is focusing on the spectroscopy. So as you know, electrons as the probe, just like X-ray and the neutron, you can do all different kinds of techniques. I will mention, hopefully it will not overwhelm you, but there are so many different kinds of method building based on the I think it's easy to start. And I actually got a lot of information from those two books in today's lecture content. So if you want to read details, please check those two books. Okay, so this is the, I think I got only 40 minutes to talk and maybe 15 minutes left for Q&A session. So I will try to go through the slides, finish all the slides within 40 minutes. But starting for developing the transmission electron microscopy, for example, the first EM was built in around like 1930s, right? And then there is a first commercial EM, and at that time, 1939, you can see the spatial resolution is only 10 nanometers. And if you know the transmission electron microscopy, nowadays, the spatial resolution can be down to tens of picometers. So, 1,000 times improved from, during the last 70 years. 45 is already, 10 times higher in terms of spatial resolution, right? So, and I'll say most of the development on the transmission electron microscope is on every single hardware from the column. So we call it the TEM column. You can see that from the very top is the electron gun, is the source, right? And in the source is actually very simple. It's just you have a like a V shape, the gun tip. because of the high electric field that you apply, so the electrons will be kind of extruded out from the electron gun, that V-shaped tip, right? Once it's extruded out, and they can be accelerated in this very high electric field. And once it reaches a very high kinetic energy, then it can pass those condenser lens. So we call it a magnetic, electromagnetic based lens. Basically, you flow some current. Those are just metal wires, right, around those lens. And once you flow the current, you see there will be a Lorentz force applied in this region, and the electrons will bend just like the convex lens using the light as the probe. So it's the same idea, right? And once it bends through all the columns, it hits your specimen or samples. And then after hitting the specimen, you have also other, intermediate lens and project lens to further magnify your image. And finally, it reaches your detector for the TEM microscope. You have the digital cameras, right? So based on the CCD. So those are the very rough introduction of the TEM column. Of course, every single component has very, very subtle details, so that you can read the books, right? I cannot go into very subtle details within 40 minutes. But I do want to point out some of the key factors that how we enable the higher spatial resolution during the last century, right? So first of all is the gun. The source of the gun, so it can be from the very beginning, it's just a metal like tungsten wave shape, right? And you can imagine that if you just use a metal and if you just use kind of like the electric field driving through, it's like the heat driving through the electrons. The electrons that you get out from the wave shape won't be that coherent, right? So if the coherency is not good, you can imagine a lot of time how we develop the gun, the source is trying to improve the coherence of those electrons coming out from a wave shape, right? So there is a shape design, and there is a design of the electric field, such forth, right? So the more coherency of the electrons you can get from the tip, the higher spatial resolution you can get from the final image plane. And the resolution basically is controlled by your wavelengths, right? It's like the light microscope that that you cannot image something lower than 100 nanometers. So it's relatively at a micrometer level. So the reason that the electron microscope can give you sub-nanometer resolution is because of the wavelengths of the electrons can be much smaller than the light, the visible light. And the reason for the smaller of the wavelengths is because of the accelerating voltage, right? So here is a very classical, with the electron wavelengths. So you can see that the higher of the voltage, the smaller of the wavelengths. So most of the modern transmission electron microscope, the accelerating voltage is higher than 100 kilovolts because we're trying to shoot for the higher spatial resolution or smaller wavelengths. The microscope I used, previously in Oak Ridge National Lab is a 200 kV, and some of the centers they have 300 kV. But there is a kind of, even we use say 60 kV, smaller accelerating voltage. At that time, then you can have to, consider other hardware to improve the resolution, but not the wavelengths of the source itself. Another thing I want to mention is that in all the columns that I talk about, the high vacuum is needed, right? So if you know the XPS, normally the XPS, inside of the chamber or the Pascal, and in TEM, the modern TEM, the number is around 10 to minus 5. So why we need such a high vacuum? So it's slightly lower than XPS, but much higher than SEM or FIP chamber that if you are familiar with. The reason is that there are two reasons, right? The first one that we want to protect those the V tip or the gun source, because those tips or filaments can be easily damaged if you have molecules, a lot of molecules around. And so we have to protect the lifetime of the gun source or the tip itself. Another thing is that we want to make sure that when the electron gets out from the gun and before hitting the sample, it doesn't deflect or reflect by any molecules inside of the chamber. And you can actually calculate the mean free path, right? The mean free path means that how long the electron can travel before hitting the next source. So of course, the longer of the mean free path, the better. Higher resolution of imaging, like sub-nanometers, you have to make sure that the total column, the whole column, is within 10 to minus 5 Pascal. So that's the requirement for the high vacuum. And this is a little schematics of the electromagnetic lens. So it's like I said, it's very similar to the light, like those convex lens, right? So the only difference is that they use the electric magnetic field. So it basically is labeled like the soft iron. It can be copper. So when it's windings together, and when you flow the current, right? When you flow a current, then you will generate an electric magnetic field. And the electric magnetic field that will deflect your electrons, just like the convex lens. And of course, the stronger the electric magnetic field that you enable in this wire can be controlled by the current density, the more deflection you can exert on those incoming electrons, and the higher magnification you can achieve. So when if some of you have a hands-on experience on TEM, so when you change the magnification knob on the machine, you're actually changing the current, right? Current density flow through the lens. It can be the condenser lens, can be the objective lens, the intermediate lens, or the projection lens. So once you change that, then you know your electron, the deflection, the extension of the deflection is changed. So the magnification can be changed accordingly, right? So that's the mechanism. So talking about the TEM, there are actually two different modes. If you read the literatures, you will find out. So one mode we call it the transmission electron mode, right? The other mode we call it the scanning transmission electron mode. So you can check the details. Those are all in the books. So the difference is that in the transmission electron or TEM mode, that this is your, so the purple color here is your specimen or sample. The beam is kind of, so this is like an exaggeration of the real plot, the real cases. The beam is more or less parallel, right? When it's hitting your specimen or sample. This is exactly like the light microscope. It's further to your image plane or diffraction pattern, right? And the only difference from those two modes is where you put your objective aperture, right? If you put your objective aperture at the back focal plane of your objective lens, then you will have an image. But if you put your objective aperture in the image plane of your objective lens, so this is your objective lens, then you will have a diffraction pattern, right? But in both modes, we call it the transmission electron microscope. Well, in the other mode, the STEM, scanning here means that when you're hitting, you can see that when the beam hit the sample, is actually focused to a point probe, right? So in this mode, is dependent on how your beam, right? The smaller of your point probe, the higher is the spatial resolution. So what happened during the imaging, collection process for this mode is that you scan your beam. Won't be higher than that, right? But you scan this 10 nanometer point probe, around your samples. You can decide how large area you want to scan, and then you can collect the signal, right? So all different detectors you can use. The A here means the angular detector. So it means the detector is not like a plane. It's like an angular shape, right? It's like a donut. So you only connect those signals from the edges from your donuts. And dark field means that you don't collect the center beam. See that you collect the center beam, right? That's why at the bright field connector, you don't have an A here because you don't have an angular, right? And why we can scan? So there is a deflection scan coil here. So basically, you can deflect the beam as what I said during the TEM mode to different directions, right? And when it deflects slightly from the original position, then you can detect the information from the different locations, and that's why you can do a scanning image of that, the interest. Familiar with ICEM, right? The difference at ICEM is the detector is sitting on the same direction on the with the specimen or the sample, but in the transmission electron microscope, the detector is below the specimen. So that's the difference compared with the ICEM. But of course, in the ICEM, your accelerating voltage is much smaller, and your spatial resolution will be much smaller than the transmission mode, right? So that's the main difference. Enable the scanning at the STM mode, that we can also enable a lot of different techniques, not only to generate the images. For example, we can collect the electrons, right? So all the electrons past a specific location of your sample can contain a lot of information of those chemical species. So the electrons will go through the kind of like scatter, right, with your materials, and based on the Z value, the energy loss will be different, right? And we can collect those energy loss electrons to different channels. So this energy filter is somehow like in the XPS system, if you are familiar with that, you can collect all those scattered electrons in this case, right, by different by the energy filter, so that the electrons intensity can be separated to different energies. And this is where that you can do EDS, just like the ICEM or EDX. You can do the EELS. So the EELS means the electron energy loss spectroscopy, as I just mentioned in this mechanism. And you can also do a EFTEM. So EFTEM here means instead of forming a spectrum, so here you're forming a spectrum, right? For each of the energy, how many electrons you deflected from the sample. But instead, you can form an image, right? You can form an image, but you can select the electrons. Say, I only need, in this case, if I study lithium metal, I only need this area, which is the characteristic peak of lithium metal, right? Let me only select those electrons from my sample. Then I know at this, say, single particle or a polycrystal region, where are the lithium metals, right? Because you might contain other phases based on the EELS spectrum. So you can select using this EFTEM technique, but based on the EELS, the electron energy loss spectroscopy. So here are some details to compare different spectroscopy work. As I said, you can use X-ray to do spectroscopy. You can use the electron to do spectroscopy. They are very similar, actually, right? So for the XAS, X-ray absorption spectroscopy, the photon or X-ray absorbed by a core electron will be excited to the outer shell, right, to the valence band. So, or conduction band, depending on where you have the electron hole, right, in the sample. So that's the basic mechanism. So in the EELS spectrum, it's the same, right? So the electron will hit your, the core level electrons and have this scattering, right? So this is of course, inelastic scattering, not like the elastic as you collect in the diffraction technique. Incident electron will lose some energy, right? And this core electron will pick up this energy and then go to the next level, right? And leave an electron hole in the core energy orbitals. So very similar to the XAS. The difference for XPS is that X-ray, this is photon the same, but this core electrons will be heated to the continuum band or vacuum level, right? It will not stay, with the within the atom, but we will be heated up to the vacuum level, and that will be the continuum band. That's the major difference compared with XAS and EELS, which that you have still have the discrete energy levels even after the electrons have been excited, right? And those are the mathematical equations I can found from those from that spectroscopy book. I won't go through those equations, but basically the square box here to simulate the U spectrum and then compare with the experimental data, right?
Minghao?
Yeah.
I have a question on this last slide. Is the difference in the sort of ionization a result of different energy levels? Because it seems with XAS and EELS, even though we're using X-rays in one case and electrons in one case, we're going to just an excited state versus like an ionized state in XPS.
So here is the thing. If you go deeper on the XPS, so the instrument level, it will align so there is a like kind of work function, right? So it's actually, when you test the samples, the instrument level, they already align your work function to the Fermi level of your samples. So actually, if you check your XPS, say you can check lithium 1s, right, compared with the lithium KH in use, it's very, very similar. The reason is that the work function is kind of canceled in the instrumental level, right? So if it's canceled, then in both cases, what you measured is the difference between the Fermi level and the core electrons. So it will be all the same.
Okay.
If there is no instrumental level cancellation, yes, you will see the XPS for a specific element will be different from the EELS, but that will be problematic because the work function is related to the instrument. You see what I mean? So if you don't cancel that, then what you will have is that if you test in different brand of the XPS instrument for the same element, you get a different binding energy, and that's a kind of artifact from the work function of that instrument. So that's why we have to cancel that part. And once it's canceled, it will be similar energy range as the EELS.
Okay, thank you. Does anybody else have any questions? Any questions from anybody? Everybody's awfully silent. Okay. All right. Well, thank you. Thank you, Minghao.
Okay, I guess I can go ahead. Yeah. So I want to mention this is a very recent development for battery field. It's called the cryo-TEM. And this cryo-TEM is not a new technique, right? So based on this, kind of a history introduced very, very early, right? So it's like 1974, first cryo-EM. But from that stage is all, applied to the biology field. And you know why? Because we want to protect the sample of biosamples under, low temperature. And it is from 2017 that this cryo method was introduced in the battery field because we found out that some of the metal, for example, the lithium metal is also beam sensitive, just like your biosamples. So we have this cryo-EM, introduced from 2017. It actually was, studied for different battery materials in the recent years in many different publications, right? Sorry. But I want to mention what is the key features for the cryo-TEM. So if you are interested in, you should always think about those three different aspects. First of all, is your sample, no matter it's from the battery field or not, beam sensitive or not, right? So if it's not beam sensitive, reduce those thermal vibrations or drifting. So it will basically, add in a lot of experimental errors in the imaging collecting, especially at a very high resolution. Another thing is that even you don't have a beam sensitive sample, if you want to explore some physical properties, for example, like superconductivity, right, or other like luminescence properties that are only shown at low temperature. The low temperature, what I mean here is not only the liquid nitrogen, right? Liquid nitrogen is what used in the typical cryo-EM for biosamples. You can even use the liquid helium, which is much, much lower. I think it's 4 Ki, in temperature. So a lot of superconductive materials can behave, can exert the properties at that low temperature. So you can also utilize cryo-EM. And the third thing is that you always need to check the instrument request. For cryo-EM is much, much heavier or normal TEM because of the thermal vibrations and drifting. So first of all, you want to control your humidity. So most of the time, even building the infrastructure like the room, right, for setting the mounting the TEM facility, it's cost even higher than the microscope itself. But microscope are already very expensive, as you all know, right? But the reason we want to do the very strict humidity control, like a 10 Celsius dew point, is because if you don't do this, during the measurement or the sample transfer or the sample preparation, you will have a lot of icing issue. So the ice will quickly, froze on your sample and damage or contaminate your samples. You don't want that to happen. And a lot of time, because the beam sensitive materials, you always need a low dose imaging, and also you want a direct electron camera. So direct electron camera is not the same as the CCD. The CCD is that you transfer the electrons to optical signal and then go back to electron counting. The optical transformation. By that, you can actually increase the signal to noise ratio by the same amount of load, by the same amount of dose. So the direct electron camera is kind of combined with the low dose imaging, right, to enable the high resolution. So if I want to build a microscope in my lab, right, those are the kind of the dream version. Yeah.
Can I ask one quick question on this last page? How, if I'm a scientist trying to do some TEM, how do I know if my sample might be beam sensitive or sensitive to beam damage?
Yeah. So the key graph you can check for a material is, if you know your material, is to check the phase diagram. Right. So the reason for, say, for lithium metal will be melted by the electron beam is because the melting temperature is. Now copper, you won't worry about those beam damage because of the melting temperature is high. So melting temperature is one thing. The other thing is that if you have heavy elements or light elements, right? If you have a light element like lithium, most of the time the electrons can hit your lithium and make the lithium out of position of the original lattice point. Then you also have a damaged materials. Say if you have a tungsten or platinum metal, you won't worry about that because it's so heavy, the electron even won't kind of kick off the original position of the atoms. So there are a bunch of considerations you need to check before you move on to, before you decide if you want to use the cryo temperature or not.
Awesome, thank you.
Okay, so this is like if I want to build a microscope, right? Like the dream version. So basically, you want all the fancy tools that I just described, but also you want this segmented detector. What you capture is the intensity difference, right? Or the intensity contrast. But in this detector, you can actually capture the phase contrast. And you know the phase contrast that can give you even more information than the intensity contrast, if you're familiar with those reciprocal transformations of the real image. And if you have a segmented detector at each of the section of the detector, so you can the more segmented, right, the more section you have on one detector. I think from the Thermo Fisher, the most developed segmented detector has 4 different sections, and in each of the section you have a different phases for one location, and you can combine those different phases to get out more information. And in this kind of imaging, you can image all the elements, including the heavy elements and the light elements, right? And we also, so this is the liquid, the cryo TEM part. You want to cool down the sample. In a lot of recent design, you don't need a holder to cool down the samples. This is like a, you side the entrance, right? But we can cool down the whole stage. At that kind of design that you can capture more samples in one experiment. We also want to enable some in situ biasing properties, because for a lot of battery studies or energy storage materials, you want to see under the voltage biasing what's the material behave there are also 4D STEM. I don't think I need to go through the details, but basically 4D STEM means, except for the 2D spatial resolution or imaging, you can also quantify the momentum space. So that's also 2D. So, plus together is called 4D. So this is the equation how we correlate the momentum phase with the spatial locations. That is cool, right? Because from the momentum space, you basically can quantify the electron density of your materials at each single location. So those are all the techniques. I want to show a real image how we do the cryo-TEM experiment, right? So this is in the UC Irvine facility. You can check the, it's called IMRI. It's open for all the UC members or even from industry. So if you are interested, you can just apply for the usage. So basically, this is a cooling holder that we can pour the liquid nitrogen. We just insert into the column. So this is the microscope. And to enable the cryo temperature imaging, we want a super stable, without any drifting or vibrations for the very high resolution imaging. So what we can do is that first of all, we have to control the temperature to be stabilized. If your temperature is keep on increasing or decreasing, you cannot stabilize your imaging for sure, right? So this is the monitor for the temperature. We also need to tilt the zone axis so that we can see the atomic resolutions. And the zone axis tilting is not something easy to do. It takes like a month to get experience on your specific sample. We also need to stop all those bubbles. So you know that in this design that even though you have a cap on this holder, that the liquid nitrogen can still contact the air, which is room temperature, right? So you will start to observe a lot of bubbles inside of the liquid nitrogen. So what we do is that we have a kind of small tube. I don't know if you can see it. Oh yeah, we have on the surface of the liquid nitrogen, then we can just extract it out from this tube. Right? By this way, of course, we have to sacrifice some of the liquid nitrogen itself, but at least we can extract out most of the bubbles so that there will be very small vibration on your final image taking. Perfect. So this is an example of the cryo-TEM image. In terms of the data analysis, right? So this is a FIB lamina sample. We can use the focused ion beam to can do the high resolution TEM. And most of the cases, as I said, that you want to analyze on your samples what are the phases, right? So in this case, we have a lithium metal and we have a lithium oxide. So we can do a FFT, Fourier transform. And based on the lattice distance, it's like XRD. You can identify if it's a lithium metal or lithium oxide, right? So we identify those two dots are representative peaks for lithium metal, 0, 1, 1, that is plain, and the do an inverse Fourier transform. So you inverse from this FFT to get the real image. And then this image will be much higher resolution than this one because you screen out a lot of noise from the original FFT pattern, right? So from this one, you can see where is my lithium metal, where is my lithium oxide. So you can see that the lithium metal is a polycrystalline here, very nano-sized domain, and in between you have a lot of lithium oxide that is generated. So this is our sample, right? The normal temperature TEM because the whole sample will be damaged by the beam. So that's the beauty. You go to the cryo temperature. And at the same time, enable high resolution atomic resolution imaging. So this is another example. This is at the STEM mode, not at the TEM mode. At STEM mode, if you use this HAADF imaging, so high angular dark field detector, what happened here is that at this imaging mode, you will see HAADF at a lot of battery published work is proportional to Z squared, right? So means the brighter of the dots here, the heavier of the elements, right? So in my sample, this is the lithium transition metal oxide. This is a layered structure. You can see the layered structure very well. And the green, so here is the structure model, right? I can overlap with my real image to show that, to showcase that how strong of the microscope can give us at the atomic resolution. So the green dots here are the lithium, and see on my samples that I cannot see lithium and oxygen because they are light elements, right? But I can resolve the transition metal very well. Because of that, I can see these layer structures very clearly, right? Because you can see that layer of lithium and then layer of transition metals very well resolved on this kind of imaging mode. And also you can see that I have some defect layers on my samples because all other layers, you can see this we call dumbbell shape or honeycomb structure. But at this two of local symmetry. So the HAADF imaging is a very strong tool to detect the defects of your sample, right? But of course, if you want to get such a high spatial resolution, you always need to tilt your samples to different zone axes. So here is an example. This is a spinel structure. If you tilt it to different zone axes, right? Let's say for any of those zone axes, if it's just a little bit off, you can see that all the atomic columns won't, and then that will influence your spatial resolution. So when you try to acquire any atomic resolution part of image, you always need to ask yourself, first of all, which zone axis you want to image, right? They all look different. And they all can give you different information. Remember that at a transmission mode that you always have a 2D projection, right? So you have to decide which projection you want to see from your particles. And strict requirement for the zone axis tilting, right? So for example, if you only have one layer of the crystal, then it doesn't matter which zone axis you tilt. There won't be any issues of overlapping from different columns because there's only one column, right? So you want your sample as thin as possible. That's why a lot of time, if we want to do very high quality imaging, we need to go to the deep lamina samples, which is thinner than 100 nanometers of all the sample regions. As easy as what just briefly talk here, it really needs a lot of experience to see through the reciprocal space and then tilt the zone axis. So this is another example of the EELS mapping of the our battery material sample. In this case, it's a zinc metal. So we can see that in our electrodeposited zinc metal, we have kind of the zinc core, and we also have some oxide layers as the ICEI. Do a mapping right on this location and this location, and then you can analyze the spectrum. So this is oxygen K edge, this is zinc L edge, and then you can map out where is location have zinc only and where is location have the oxygen. So you can generate those EELS maps, which is very similar to the EDS or EDX maps. I think all of you are familiar with in the SEM technique. So for EELS, it's not only mapping out the different elements in your samples, but also give you all other chemical bonding information, right? So in a typical EELS spectrum, you have different regions. You have the zero loss peak. Zero loss peak means that the electrons get through your sample without inelastic scattering with your atoms. There is a chance of that, and this is zero loss peak. We oftentimes use this zero loss peak to align the spectrum, right? And we also have this plasma region. So this plasma region can help you quantify or plasmons you generated the secret of your sample, right? And it's quite intuitive. And then we can go through this, we call it EELS, right? This is very similar to the ZINs if you're familiar with XAS technique. And in this region, you can quantify, say, for example, the oxidation state of the transition metals, and also try to quantify the bondings of that transition metals. So I will give you some examples, right? So this is very well known in the, it's a kind of a volcano shape of the versus the, so the x-axis here is the d occupancy, because for one transition metal, if you have a different oxidation state, if you have a different amount of d occupancy, d electrons occupancy, right? And you can see that we can quantify through this L3 to L2 white lines intensity ratio, right? So here is an example that if I have a different d occupancies, I should get a different L3 to L. I can quantify the oxidation state, right? So here is an example how we can quantify the intensity ratio of L3 and L2 peaks. So here is an example of the manganese LH. And once you get this, I mean, you can check the book why we use this called a step function. There's a reason for that. And for different elements, for different edges, you will have different mathematical model for the background subtractions. But after this background subtractions, then do a mathematic divide of L3 over L2, and that will be the intensity ratio I mentioned here on the y-axis, and then you can further quantify how many d electrons at that transition metal and what is the oxidation state, right? So this is
so I have a quick question. So for this, is it not possible to do what you do in like XCS or XPS and just look at where those the energies of the transitions lie, and at a higher oxidation state will increase in energy?
Yeah. So a lot of papers they don't do this detailed quantification to claim the oxidation state, but they check what we call the shifting of the peaks, right, in the energy value.
Yes, yes.
The reason I don't prefer that method, because you always need to consider the energy resolution of the technique. So for XAS and XPS, the energy resolution can be down to, I believe, 10 milli electron volt. At that level, the shifting makes sense to me, because a lot of times or cases that even there is the oxidation state change, your shifting of the peaks is well within, say, 100.1 electron volt. But in the use, because most of the microscope you don't have a monochromator, if you can be as high, I mean, can be as low as 1 electron volt, right? In my cases, the best I can achieve in on campus at UCSD is about 0.75 electron volt. So that means 750 milli electron volt. In that case, even you see the shifting of your peaks, I don't think it's a very trustworthy method to argue the oxidation state changes. If you have a very advanced microscope, like in UC Irvine, they have I think they have a Neon, right? So Neon is a totally different brand of TEM microscope. It's designed for the monochromic electrons. At that microscope, you can down to several milli electron volts, so even higher resolution compared with XPS and XAS. Then you can certainly claim based on the peak shifting. So this is an atomic resolution used mapping combined with the HAADF imaging, right? So what I can do here is that I do a HAADF imaging. I get the transition metals, those items, and then I can do the use mapping, right? I can see atomic layer by atomic layer what is the transition metal, in this case manganese oxidation state, and utilize the technique I just introduced. You can quantify the L3 to L2 ratios, and then you can see this transition metal changes, throughout my surface and my inner subsurface regions, such forth. And you can correlate with any, in this case, any disorder regions generate or defect regions generate on my surface. It can be generated during the synthesis or after electrochemical cycling, but that's nice because you have both structure-wise information combined with chemical information, right? So this will be my last slide. To finish, I want to point out, although I introduced a lot of advantages and why you want to study the TEM or you want to do the TEM experiment, I want to remind you that there is also some disadvantage of this technique. First of all, the damage, right? So you can see that this is for sensitive materials. If I don't use the cloud temperature, you can see damages, those holes generated by the electron beam at the STEM mode very easily. So you always need to, when you report the data in the literature or in any kind of publications, you always have to make sure that your sample is not damaged for the data collection region. Right? So this is one of the things you always need to bear in mind. Another thing is that when you quantify, so if you only need to qualitatively tell what happened for my structure, then it's relatively easy. But whenever you want to conversations, you always need to do some sort of simulations of fittings, or else all the signal will be influenced, for example, by the thickness, by your microscope alignment, such forth. So, but the quantification, the fitting of first principle calculation itself is not easy to do. It may be even harder than the data collection itself. So it do take time, right? So if you want to really go deep into this technique, I think there are a lot other, Another thing is that if we want to, so a lot of people criticize TEM, you only have local information, right? Because you only focus on one particles, one very high resolution regions. But if you want, we can actually enable statistics for TEM. And the methodology is that you can, in a lot of microscope, there is now automation collecting of the data. So you can move the beam from one location to the other location and such and so on. And a lot of images for all other different locations. But by that way, you will generate a lot of data, right, in terabyte size or gigabyte size. So once you have so much amount of data, what we need to utilize is the machine learning technique for data processing and analysis. You certainly cannot do manual way anymore if you have a lot of data. It's just not possible, right? So there is a trend in recent years. Machine learning of the image processing is a very hot topic, and I hope that in the next 10 years there will be less criticism on the statistics of the TEM technique, that we can enable sort of very large view together with the high resolution imaging. That will be very cool for the TEM field. I think with that I can finish here, and I can take more questions if you have.
Thank you so much, Minghao. I want to open it up to anybody in the audience. Please ask away.
So this EELS oxidation mapping, are you able to run operando, or have you run operando studies on like the oxidation state change?
Yeah, we did a operando study. You can check our group website. Like I think it's in 2017. It's a nanoletters. What we do is that it's a solid state battery, right? So we have I think it's lithium as the electrolyte, and we have a silicon as the anode, and lithium cobalt oxide as the cathode. And once we started the biosing, it's not cryo-based because the lithium cobalt oxide is quite a beam stable, not that sensitive. And when we start the biosing, then we can capture the cobalt oxidation state change during the biosing. Yeah.
Mm-hmm. Okay, that's interesting.
How is the energy of the electrons actually affected by the biasing in that process? Because I would imagine you're introducing a lot of electrons through the actual cycling of a battery.
Yeah. So first of all, personally, I don't have a strong proof saying how much of the biasing will induce to the electron diffractions when upon heating the samples. But what typically did or do in this field is that you want to collect the information from the dark current condition. So what I mean is that you bias your sample, right? And when you bias your sample, you can turn off your beam, right? You just do the biasing, and you can hold the voltage for some certain amount, and then you open the beam. So you can make sure that your electrons not flow very fast through the imaging process. So that's called the kind of dark current processing. Yeah, so if you want to do a real operando measurement, you have to consider the function of the electric field through the biasing. But I don't think anybody knows how much actually we induced to the electrons, incident electrons.
Okay, so in the operando measurement you're talking about would be basically you would stop the biasing the time that you take your measurement and then you would resume it.
Yeah, if you really worry about the coupling between your biasing current and the electrons, I think you have to do that, right?
Okay, thank you. Any other questions? All right. Well, I'm gonna quit the recording here.